So today I want to talk about a second order differential equation, and honestly speaking, it is a subject in itself. Really, I'm telling, like, wow, I thought it's just a differential equation because we have so many differential equations. It's just one of them, a second order one, but no, it's just not. It's not just a differential second order. It's a lot. It's a lot. So suppose I have so any second order differential equation can be written in this form, the most general form possible. This is the most general form possible, and uh, it is a subject in itself, as I said. And if there is nothing in this side, then we can write it like this. And you might be wondering, why is nothing multiplied by here? Well, uh, for some reason mathematicians just like clean here, and they just divide whatever was here about with this, and you just get a clean one here. So now if I further reduce this, I mean, not reduce this, the special case of this is this. This is a special case, and what should I say, man? Like, it is so crazy. I don't know what more to say. I just it just Today I just got lost while studying all this. Honestly, I will right now. I will just talk about the homogeneous. This is called homogeneous. If there is no function in the right hand side, everywhere if it is if some function is just getting multiplied with y or its derivative, you call it homogeneous. Non-homogeneous means there is a, I don't know why these names, there are reasons, but I don't want to go there. I just want to see how things work. And then so the thing is, one of the ways to solve this differential equation is pretty nice. So one of the ways is, uh, so suppose you can assume that, let's say that this differential equation is a linear combination of all the uh, monomials. I should say that's a lame word, but all powers of n, because the thing is x power n can form a basis in this space of real numbers functions. And I if I assume that, okay, any function in this space continuous, good, finite enough, I can write it as a linear combination of these, then that will be very good. So if I do this, what I have to do is, uh, yeah, also, oh yeah, apparently I can only do this if, I think if these are themselves polynomials. If they are not polynomials, if they are like sin x cos x, it will be very difficult. And let me try solving one of the differential equations if they have given any. So here is my book, Arfken book. um, so here it is. Let's see what they have got for me. Something related to singular points. I should have focused on this, but I didn't. I will study these later, singular points. So right now I will focus on this. uh, so how does this work exactly? Let me go a little more above, see if there is something more important and interesting. Honestly, everything here is interesting, and it's kind of huge, like the top. You might spend years studying this. I feel now like there is so much to grasp, so much to cover, so much to understand. It just uh, let's see what do we got. First order are not that interesting. I mean, they are interesting. Yeah, all of them are interesting, honestly. Uh, uh, so this is not something I can, learn in a month or a day, but uh, let's. So there is something called singular points. I ignored this today. I should have studied this. Uh, I think it is a simple concept. Let us look at this and then maybe. So, what is this exactly? Hmm, okay. Okay. Okay, no, I should spend time here. I can't just whatever I know today, whatever I learned today, I will explain. Uh, so okay, he's solving this differential equation. So let us do this as itself. And anybody in his undergraduate has solved this. If he hasn't solved it, I mean, anybody in his maths or physics undergrad must have solved this in his life. If he hasn't, his undergrad hasn't went well. So let us do this. So here we have it. Now, so if I assume that the solution of this differential equation is a linear combination of all the polynomials, if I assume this, okay, so first of all, I have to differentiate this thing twice, and also if I expand this, this will be something like c naught c1 of x, c2 of x square, so on. That's what this means. And if I differentiate this once, so what happens is something like this. And now if you see that if I take 0, this will become 1 by x, but 1 by x is not allowed in my function. I don't want that. So what I will do is instead I will start this series itself as 1 by x does not exist in my uh, what should I say, linear expansion. So this will be something like this, c0 times 0 because it's gone, plus, okay, no, not even needed this is something like c1 times x naught plus I just differentiate this c2 times 2 times x and so on, just a different classic differentiation. And now let us go next. So a second order, because that is what I need. So if I differentiate this again, this will be, so again one more term will vanish, so I will just write this n times n minus 1 times cn times x power n minus 2, and this will look something like c1 is gone now, c2 times 2, c3 times 2 times 3 x plus c4 times 4 times 3, I guess, Wait, am I doing it right? I think I am doing it right. Pattern is a little off, but it's good enough. And then now it will be x square, of course, and it just keeps going. Uh, Now I know that this is the case, right? D square y by dx square plus omega square y equals to 0, and I know what are the values of these. And if I just substitute this, so if I just write what is d square y by dx square now, it is summation from n equals to 2 to infinity n times n minus 1 x power n minus 2 plus uh, omega square times summation n equals to 0 to infinity x cn times x power n. Now the thing is, I have to match the powers of this. So one of the ways I can do is, you know, I need x power n here, right? And I know that again, even here it is like something like this, a number with a constant number plus some other number with x power 1, some other number with x square. It is going in nice order like 0 1 2 3, but the indexes are a little odd, right? So the thing is, this the my series starts with this power being 0 initially, and then it becomes 1, it becomes 2, and everything. So the best so the very nice and neat thing about this is, I will, wherever I see n, I will just shift it by n plus 2, and everything will be perfectly the same, nothing will change. So I will just write n equals to 0, infinity, so n plus 2, and this will become n plus 1 of x power n plus omega square summation n equals to 0 to infinity. uh, and also remember, yeah, I didn't told this, uh, if whenever you shift this, the question will be, okay, if I shift, what should be the limit here, right? Here it should be 0, because that is what I want these limits to match. So now